The Electronic Alliance brings you another in a series of technical presentations to continually educate you in product design and manufacturing. Today's session is about microcontrollers, choices and design methods. We welcome Jan van Niekerk, Senior Partner of RF Ops. Anytime you need to find qualified sources for your design and manufacturing needs, contact the Electronics Alliance.
Thank you, Gary. Well, good afternoon, everybody. My name is Jan van Niekerk. When Gary asked me to do this presentation, I kind of thought on, since we are time constrained, what are kind of the 10 most important things that you should think about when you do microcontroller design. So you can see there I have 10 little circles, and we're going to kind of go around clockwise and look at each of them. And I thought to start out with, one of the 10 things is know who the presenter is, because then you can kind of get a perspective of my perspective and weigh what I'm saying with my background and everything. So you're going to start a little bit first with the presenter. And Mike and Gary, if you guys can time me, I need to take about 4 minutes per slide. So if I talk too long, just hurry me along. So here's the presenter history in microcontrollers. So I'll actually show you guys the next slide there. That is a room of my friend's house in '78, where I spent probably more time than at my own house, where we were building this Z80 controller. It was a year after the Z80 came out. We used all the money that we ever saved to buy the Z80 and some RAM. And you can see over there, do I have a mouse here? You can see over there are 2 bread pans with the power supplies in them. I'm happy to tell you guys that this, as you can see, doesn't have much organization skills here. This guy married a librarian, and they lived happily ever after. Okay, so fundamentally, as a young guy, we built that Z80, as a team in my friend's room. I moved on as a student to work on the TMS 320. In fact, one of the first TMS 320s from TI that came to South Africa, where I was born and where I was a student. Then I was in a software programming startup where my job was to write Intel 86 assembly language. 2 years later, I found myself in another startup where I had to write a lot of 8051 code, and then we discovered the microchip PIC, and we started programming in that. This company was eventually purchased by Microchip, and I moved from South Africa to Arizona to work for Microchip, where I worked for just about 9 years on the PIC, and learned about corporate America and the world of silicon manufacturers and microcontrollers, which was a fascinating experience. Then I moved to Texas, being recruited by a good friend of mine, and worked for another semiconductor maker for many years, Maxim, just here down the street, where I worked with the Max-Q microcontroller. From there, I moved to another startup where we worked on an ASIC, which was RFID. So this kind of started focusing on my RF experience. I've always, since I've been a radio amateur, I've always kept an interest in RF, and actually right there at the startup in '88, I started working in RF as well. So almost all those had some RF aspect coupled with the microcontroller. We've been busy at RF Ops. We've been working with the ARM Cortex M0 microcontroller for quite a while. So that's your presenter. So I'm a micro guy. I'm also an RF guy, and I've seen a lot and I've learned a lot about the semiconductor world. So actually, when you design a microcontroller, and actually when you purchase a microcontroller, from a vendor, it's good and important to understand a little bit about the world of silicon, because you're purchasing essentially a small piece of silicon, and to understand what you're buying and what the value is, and how semiconductor makers think is really important in negotiating, etc. So I wrote down a few things, and right here on the left-hand side, I show a silicon ingot. That thing is a foot in diameter, and it's taller than a man, and you can imagine that it weighs hundreds or maybe thousands of pounds. But the interesting thing is that is absolutely the purest man-made substance that is made in large quantities. That silicon is so refined, yeah, it's hard to imagine how pure that stuff is. The impurities, especially boron there, is less than 10 to the minus 13. And the chemical processes to get to that is absolutely fascinating and, worth a talk on its own. But this is pure stuff, and then of course that thick pillar of silicon is cut up with diamond saws into tiny slices, and that becomes essentially the material, the paper that silicon manufacturers print on. And silicon manufacturers, that's really what they want to do, and that's what they're good at, and that's what they set up to make money of, is that they print on those wafers. Now the interesting thing is that even though the dimensions of what we're putting on those wafers are shrinking, and the density what we're putting in is getting denser and denser all the time, in reality the wafer obviously always stays the same and costs the same. So a thin slice of that wafer that's being processed costs somewhere between $1,000 and $2,000, and has cost that, many moons ago, and still costs that. Of course, what we're getting is, as those geometries are shrinking, we are getting more value for the money all the time. So to give you an idea, these days in 65 nanometer, which is kind of on the back end, the modern technologies are coming down to 40 nanometers, and the bleeding edge these days is 20 and 12 nanometers. A 32-bit CPU has the fascinating area of about 0.2 square millimeter. And to give you an idea, 128 kilobyte RAM is, 1 square millimeter. So when you buy this, keep that in mind. What are you paying for? When you buy a 32-bit microcontroller with 65 nanometer, 128 kilobytes of RAM, you're essentially buying about 1.2 square millimeters of silicon. Now to give you an idea, since that wafer is fixed cost, we know that a square millimeter of silicon is fixed cost, and the fixed cost for that silicon is roughly between 1 and 2 pennies per square millimeter. So the real cost of the silicon itself is, in the order for that microcontroller between 1 and 2 pennies, and what else the microcontroller maker is asking you is for the packaging and the testing and of course the money that he's making. So one of those wafers that's a foot in diameter, 300 millimeter in diameter, is about 70,000 square millimeter. So if they have a small CPU and some RAM that they put in there, they can typically extract, a significant fraction of 70,000 of those little chips out of a single wafer, which cost them between, $1,000 and $2,000. So that wafer cost is fixed. And then just again, the reminder, Moore's law, Gordon Moore of Intel's law, that says the density goes down by about a factor 2 every 2 years, which is absolutely fascinating because we are the benefactors from that. Every 2 years we get 2 times more out of silicon than what we previously got. Now, I just want to make the point there that we're right about to hit the bottom end on that, because even at 20 nanometers, the horizontal spacing is not truly the issue. The problem is that the oxide thickness, which is much thinner than the planar dimensions, is getting to the 1 nanometer region. And the problem is that in a silicon lattice, the atoms are about 0.5 nanometers apart. So you can see that we're at the point where the oxides are now 3 atoms thick. So basically we're hitting the bottom in the vertical dimension. And just to make another very important point is that leakage in silicon, as you shrink all these dimensions, is becoming significant. So in your Pentium processor, about half the energy in the Pentium processor is just going to waste and to heat because of the current that's leaking like a sieve through all the gates to the bottom of the chip. So the latest technology says that we go from planar field effect transistors and we flip them on their side so that they stand up, and that is how Intel and the top manufacturers have reduced that leakage and allowed them to go from the 100 nanometers down to the 20 nanometer technology. So there's some technology where the leakage is minimum, and where to us the leakage current is important because that's the standby current of our microcontroller. So anyway, just a perspective on the silicon, which I think is good and handy when you think on what you're purchasing when you buy a microcontroller. And then I'm going to talk a little bit about the architecture, and somebody here said, well, I'd like to find out a little bit more about architecture choices. Now, I kind of want to warn you guys that when I looked at it, the architecture choice today is so overwhelming that it's actually simple, and we'll see why. So the first question is how many bits, right? So we started off with 4-bit microcontrollers, we went to 8-bit microcontrollers, and 16, and now it's 32 and 64. So why is it that we want more bits? And the answer, the fundamental answer to that is that the address, the registers that you use for an address, should not be really special. So the arithmetic that you do in your normal integers and the arithmetic that you do for your addresses should be the same, and there should be no special case and paging. And because of that, the real question on how big our microcontrollers and our bit size is, how big is your memory? So if you think about the memory stick that you carry in your pocket today, it's probably somewhere between 4 and 32 and 64 gigabyte. And just as a reminder there, 4 gigabyte is 32 bits. So we're right at that tipping point today where 32 bits is probably starting to be a little on the low side for the memory sizes that we have. So I'm going to go out on a limb here and say in a few years, when process nodes shrink another few factors of 2, and the guys figure out how to get how to beat that thin oxide problem, we're going to see 64-bit embedded microcontrollers, and they're going to address large portions of memory. But anyway, for our discussion here, for most applications that I've seen in my life, 4 gigabyte of program memory and data memory is more than enough. And so today I'm going to talk about 32-bit microcontrollers, and I'm going to recommend that unless you do something very special, that you look at 32-bit microcontrollers as well. So that's the bit answer. Now, the other question is CISC or RISC, complex instruction set computers or reduced instruction set computers. In the late 1980s, DARPA launched a project to say we want to get some academical research done to find out how can we make better controllers. And actually, Stanford and just 40 miles away at Berkeley, 2 California universities came up with 2 very similar conclusions, where they said this new concept of a reduced instruction set computer, and the fundamental premise of that is that you have simpler instructions, but you then have to execute more of them because the instructions are not complex. But the bottom line is that the sum total of that actually increases the performance of the microcontroller. So out of that came the MIPS microcontroller from Stanford, and A small company in England, Acorn, which were the makers of the BBC Micro, got hold of the Berkeley paper, and they were at that point looking at the Motorola 68000 microcontroller and found it kind of lacking for what they wanted to do. They at that point they already figured out that they wanted a 32-bit microcontroller. And they read the Berkeley paper, got very excited, and decided that they're going to make their own microcontroller. They're going to design their own microcontroller based on the Berkeley. This is just around 1980. And by 2001, so that's 20 years later, we have, viable products in a 32-bit microcontroller. And the Game Boy Advance here is one example of, an absolute success of these microcontrollers that just display how superior this architecture was. They sold 80 million of them. It was an ARM7. It ran at 16 megahertz, ran off 2 AA batteries. Could run off those AA batteries for 15 hours and had 352K of RAM on them. And it's typically products like these, so that the processor inside there was licensed from ARM. This was the type of product that proved to the world and to ARM that this is, an architecture that very well balances the cost of the microcontroller with the energy consumption. And of course, when you look at the games that were actually running on those processors, they for their time were an absolute technological marvel. And of course, that's just one of them, and there were several follow-ups to these. And today, there's about 1,000 ARM licensees, and hundreds of companies that actually implement ARM products. An interesting point here is, why did MIPS not? These two architectures are very similar. Why did ARM have that fantastic success and MIPS didn't? And I don't understand the question to that. I guess it's just marketing. But somehow, the ARM was probably first mover advantage or something like that. But I could never find a compelling reason where you can say, well, it sucked at this. And in fact, MIPS was just recently bought by, I think, Image Technologies, and they're trying again to make a comeback in the market. But of course, ARM is just so far ahead. When you want to go and purchase a microcontroller, an ARM 32-bit ARM microcontroller today, which is what I'm recommending, you're going to have a large choice of vendors to get the silicon from. And I'm going to show you a list. So this is IC Insight's top 10 and top 20 silicon manufacturers in the world. So literally, this is not microcontroller, it's just literally semiconductor makers by revenue. And you can see there the 47, 33, 17 is the billions of dollars of annual revenue of those companies. And of course, right at the top is Intel. And the top 10 of them there essentially is about half the semiconductors that are made in the world annually. Now on the right-hand side, I kind of wrote down what kind of ARM activity is going on at that vendor. And as you can see, for all but two of them, which is number 4 Micron and number 5 Hynix, they're making some kind of an ARM processor. So on that first page, 8 of the top 10 semiconductor makers in the world today manufacture some kind of an ARM. So Intel calls there's the X scale. Intel actually has an ARM architectural license, which is, the top class license that you can get from ARM. And they actually have, real ARM-based processors. In fact, their X scale is an ARM5. And so you can go down here, Qualcomm, the famous cell phone company, they're using their latest technology is called the Snapdragon, and that again is an ARM7. And you can go down the list here, and so these are very illustrious, the top of the semiconductor world, and all but two of them And by the way, those two, Micron and Hynix, they don't really make microcontrollers. They're memory guys, and that's why they don't make processors. But anybody who really makes processors today makes an ARM too. That's kind of the point. So ARM has somehow literally overwhelmed the microcontroller world. There's the next 10, number 11 to 20, sorted by annual revenue. And again, on the right-hand side, you can see each of them literally, again, make some ARM products. The 10 on the top page, I think, maybe except for ST Micro, which is kind of coming to the point where the small guys like us can talk to them, or actually can go to a semiconductor distributor and buy chips from them. Well, I guess Texas as well. So just about number 7 is about the minimum gorilla size where, you know, a small company can go to and actually purchase microcontrollers. But the rest of them there, NXP, Freescale, On Semiconductor, you know, are the type of vendors that when you're interested and you're looking at the distributor, you're going to see stock of their parts at the vendor. And then finally, vendor-wise, there are 3 smaller vendors, and Microchip, especially because I used to work with them, but they don't have any ARMs. That's very interesting. They made a very tactical decision, and they talked to MIPS, and so the Microchip 32-bit microcontroller is a MIPS machine. And it will be very interesting to see in the long run, you know, how they fare, because it's a complete exception compared to the other guys. And then, of course, 2 smaller companies, Atmel, 1.4 billion revenue per year. They make a whole slew of ARMs, M0s, M3s, and M4s. And Silicon Labs, right here in Texas, is very interesting because they recently purchased Energy Micro, which was a startup company. I forgot where in Europe they're from. Norway. Gearfora, the guy who started Chipcon, which was sold to TI. So his second endeavor was Energy Micro. I think he learned while he was at Chipcon that there's a need for a super low energy microcontroller. So he implemented a few of the ARM CPUs and called it Energy Micro, and that was recently purchased by Silicon Labs. So roughly that's a vendor perspective. So of the top 20 vendors in the world, 18 of them make ARM processors, and a handful of them are the guys that we would typically go talk to if we want to buy a chip. Okay, I just want to say a few things about performance, because when you implement a microcontroller, one of the questions is, can this thing perform? Now, we don't really have enough time here to completely talk about performance, but there are 2 things that I want to say that can give the guy in the street, you know, a fairly quick access to get an idea of how is a specific microcontroller performing. And one is called the dry stone test. The other one is called the core mark test. Now, just to sum up, these 2 are just 2 small C programs that anybody can go download from the web. It will take you 5 minutes of Google search and you'll have the source code. And you can go compile that for any microcontroller that you're interested in, run it, and it will tell you, it will print out the core mark for that specific microcontroller. So the real point is, you know, one of the very simple things that you can do if you're interested is to actually download the dry stone, compile it and run it, or download the core mark test and compile it and run it. But the good news is if you just Google a little further, you'll find 4 or 5 sites where you know, somebody with some extra time has, you know, essentially benchmarked every controller, and ARM themselves publish a bunch of this. So just by a simple Google search, you can find a good summary and comparison of the performance of these microcontrollers. Now, I'll just preempt it for you to say that there's none of them that are spectacularly better than the others. They kind of perform like what you would expect, right? More or less all the same. I just wanted to say a little bit about the dry stone, just give you a little bit of background on it as well. A DMIP, which is a dry stone MIP, is the number of iterations number of dry stone iterations that you can have in a second divided by 1757. And the reason for that is in the old days, when they ran this on a VAX 11780, which is that big box that you see there on the right-hand side, that VAX 11780 cranked 1757 dry stones per second. So, and that was a 1 MIPS VAC. So if you divide by 1757, you're essentially comparing yourself to a 1 MIP VAX machine. Now, to give you an idea, ARM Cortex-M0 runs at 0.93 DMIPS per megahertz. So if you run that thing at 1 megahertz, you have the same processing power as that VAX 11, roughly the same processing power as that large VAX 11780 on a chip that is literally 0.2 square millimeters big. So that's how far we've come, in 30 years. It's just absolutely astounding. And just to make another point there, you can see that the M3 is slightly more efficient because the pipeline is deeper, so things are executing more in parallel. So the M3 will give you 1.25 DMIPS per megahertz, and the A7 and the A9, which is, state-of-the-art, extremely long pipeline, modern ARM designs. So they're just making the pipeline longer and executing more things in parallel, get to 3 DMIPS per megahertz. So between the very simple Cortex-M0, which is about 10,000 gates when you go implement it, and the A9, which is 100,000 gates, there's a 1 to 3 performance. So 10 times more silicon, but 3 times more performance. And just as an interesting reference, in 1981, the $3,000 4.77 megahertz IBM PC ran about 390 dry stones per second. So I guess if you divide 390 by 1757 IBM PC, and then you have to divide by 4.77 megahertz as well, probably something like a 0.01 DMIP. So this piece of ARM Cortex-M0 is probably 30 times faster than the 1981 $3,000 IBM PC. So it's just absolutely fascinating what we're getting today and what we can do. And another performance point that I want to make is when you design a microcontroller, the question is how much spare processing power should you have in it? And you guys can go read it a little bit. It's called, look up on the internet, it's called CPU utilization. And your microcontroller should roughly idle around, or your microcontroller should not be busier than about 70% of the time if you're doing typical scheduling in a microcontroller. So don't go design your embedded system where the microcontroller is 99.99% busy, because you're going to run into trouble. So just be aware of that when you go design. There are a school of people that say that your micro should be about 50% idle, and I'm with them. Err on the conservative side. So if you go calculate that you need so much processing power, go get a micro that can do twice that, and then you'll be safe. The next point is the edge, and the edge is kind of a new modern word to say, well, what happens on the edge of the CPU, which is of course the I/O and all the connectivity. And I don't want to say too much about it, but of course those are some of the critical elements when you select a microcontroller. And so some of the things that I've learned in my experience, some of the key things I'm putting down here. Obviously, depending on how many things you want to do, how many pins you need to wiggle, when you select a microcontroller, consider how many. Don't just go buy a microcontroller that if you want to toggle 4 things have 4 pins on it. Make sure that you have spare pins, because pins don't typically all do the same thing. They have different behaviors. Some of them have pull-ups and pull-downs, and others don't. Some of them have interrupts on them. So you have to carefully go study what you need, and also make sure you have some spare pins. also be forward-looking in your peripheral selection. If you need 2 serial ports and your next project is going to need 3 serial ports, that serial port is, it's 10 cents on the cost of the micro. So when you decide on your peripheral selection, think of what you're going to need for your next 2 or 3 projects and put it in there, because essentially you're getting that silicon for free. And then you don't have to change microcontroller or architecture when you do your next project. There's a very important one which I call vendor lock. So you'll find, I just saw a classical example of that just a few days ago, where one vendor said, I'm doing this ARM processor, but I'm putting in this very special peripheral. And of course, if you fall for that, right at that point, that vendor has you locked. So you have, 20 or 30 vendors that you can choose from for your microcontroller. But if you choose a very special peripheral from a very special vendor, then you're locked to that vendor and he can decide what he wants to charge you, because you can't go anywhere. Since I've worked on the vendor side, I've seen that. The vendor wants you to fall in love with his special peripheral, because then he can charge you whatever he wants. There's no competition. So when you choose a microcontroller where you can have something similar from 2 vendors. So then you can go, well, A says he's going to charge me that, and so then you can go to B and say, well, he's charging me, and play the vendors off against each other. The other thing is that peripherals consume power and clocks, so that's important to remember. If you're energy constrained, peripherals that are running actually consume energy. Now the good news is, in the ARM architecture, you can often turn peripherals off when you're not using them. Now when vendors license the ARM core from ARM and they put their own peripherals in, they get a really nice core from ARM that has been debugged by thousands of users. But then they go put their own CAN bus or whatever they put around the ARM core in there. And that is not always as well debugged as the ARM core itself. So often vendor peripherals are much more buggy than the ARM core itself. So the first thing when you go select a microcontroller and you're thinking, I need, for instance, let's say CAN bus, immediately you go pull the errata sheet from that vendor and you go through the errata sheet and you go read if their CAN bus actually works as advertised. And very often you'll find they say, well, on the CAN bus peripheral, when this message comes in, there's a bug, blah, blah, blah. And then you have to figure out, is that important for you to implement your product, or is that a showstopper? You want to find that out before you do the board layout and the software and all of that. Then the other thing on the edge is, do you have any special processing needs that typically take up a lot of software, such as the AES encryption algorithm? And then you have to consider, do I actually want to get vendor lock? Because obviously if you say, well, this vendor has the AES algorithm implemented in hardware, and it's the only vendor that has it implemented in hardware, then yes, it will save you power, but you're going to be locked into the vendor. So then you have to consciously make that decision and trade off. Is it important enough for you to deal with the vendor lock? The good thing is you can, let's say, find 2 or 3 vendors that has the AES algorithm in, then you're home free, because you get the benefit of a special processing peripheral without being locked into a specific vendor. And then another interesting thing that we ran into is that if you have something like an encryption algorithm embedded in a microcontroller, you could run into export issues under the International Trade and Armament Agreement. And the AES algorithm is one of those where you need to get special permission to export them from the US. And no, you cannot sell them in Libya. Okay, so that's kind of just a very brief perspective on the edge and peripherals. So as we go around and you think about the vendor and the silicon, the next thing that you got to think about is, your peripheral set and your pins. And just a final caveat, which, when I worked at Microchip, this is something that when you're on the vendor side, you see it a lot. And that is the crystal that you're putting on your microcontroller is a trap for the unwary. Because you go, okay, microcontroller and a crystal, I stick them together and they oscillate. But how do you know that they will oscillate forever? And how do you know that, that they will oscillate at minus 20 degrees centigrade? And how do you know that they will oscillate when the next batch of microcontrollers come from your vendor, where, the guy tweaked the needle with the boron deposit, slightly, and the gain of the little amplifier in there that runs the oscillator is, 10% lower. So the process skew from the microcontrollers and temperature and also variance in the crystals. You might get a batch of crystals from the vendor, and the next batch you get the series resistance unknown to you is 10% higher than the first batch that you got when you qualified these. So it's an absolute trap that you have to be very careful of. And so when you are going to put in a crystal, make sure that you talk to the vendor of the CPU and to the crystal maker, and make 100% sure that if you're not the expert on that somebody who knows what's going on signs off on that. I'm going to use this crystal with this microcontroller. So just be aware of that. And in fact, if you want to be 100% safe, buy a crystal oscillator. It's well worth that extra 10 or 20 cents, because the guy who sells you a crystal oscillator, he has to warranty that that thing always works. So then it's not your worry. But anyway, I know for a cost thing, we like to put the crystal on, but don't just slap a crystal on that board. It's a trap. So be careful. And actually, to do that, since I've been through that process, just want to make the point to make sure that a crystal and the microcontroller actually work together well is literally months of careful engineering, because you really have to understand the spec of the crystal maker, and you have to understand the spec of the microcontroller maker, and the right specs is sometimes very difficult to get out of those two parties. And then the other thing is, if something goes wrong, who's responsible? Then finally, I just want to talk a little bit about the energy, because the microcontroller needs energy to run. So a couple of points on that is that roughly current is a linear function of the clock. So at this point, microcontrollers, the typical microcontrollers that we're talking about, runs between 0.1 and 0.2 milliamps per megahertz. If you're running at 10 megahertz, it's going to draw about 2 milliamps, or somewhere between 1 and 2 milliamps. So it's good insight to understand that the current is linear. Also a warning that current is highly nonlinear with temperature. So you design something for somebody, you calculate that on a battery it's going to last for a month, but then you find out to your surprise when you leave it out in the sun, it only lasts for a week. And the reason for that is that highly nonlinear increase in current. So go look, your microcontroller datasheet says current at 20 degrees centigrade, but make sure you find out, if that's important to you, what is the current at 40 degrees centigrade, and I can guarantee you it's going to be a lot more. So why is all this important? Because modern electronics is untethered, so it's running off batteries. It needs long battery life, or it needs a smaller battery to make it smaller. So once again, a battery, as soon as somebody tells you put a battery on the microcontroller, your hair should stand on end, because it's a trap for the unwary if you want to make a successful commercial product. The battery has an end voltage that is very different from the specified voltage of the battery, and if you find that out late in the project, the battery can easily cost more than all the other electronics put together. I'll give you an example. That Tadiran battery that you see over there, that works from minus 40 to plus 125 degrees centigrade, it's an AA cell. That little AA cell would cost you around $6. So that's more than your that's more than 3 microcontrollers will cost you. So again, make sure you do your battery homework. And temperature, temperature is one of the key issues. I guess, yeah, here it is. So the capacity is very current dependent. In other words, if you draw more current out of a battery, it's actually depletes faster than what you thought. It's also heavy temperature dependent. If the battery is cold, it will never give its specified capacity. And if you think you can test that in a temperature oven, good luck, because it will literally take you months to test. It's very hard to accelerate these tests and get to realistic results. And then the other thing with batteries is, if you just take a normal, coin cell and you put it at a high temperature, you'll find that within a month the coin cell is completely depleted. As soon as you go to a little bit higher temperature than what they recommend that the coin cell should be stored, the coin cell leaks like a sieve. So you got to be aware of all that. So the temperature range, not only where you operate the thing, but where you store it is critical. You put these in an air-conditioned shed in the Arizona desert, and within a month they're all flat before you even installed them. Another important point is, as soon as you make these cells hot, their peak voltage goes up. For instance, that Tadiran cell that I showed you previously, that cell voltage is about 3.6 volts, but if you heat it up a little bit to 80 degrees, it goes to 3.74 volts, which is above the 3.6 volt absolute maximum voltage specified by many microcontroller makers. So if you want to put those two together and you're in the Arizona desert, all bets are off on the reliability of that product. So you got to be aware of all of these. And then the end voltage, of course, when the battery is going down, typical lithium cell end voltage is 2 volts or maybe a little lower, 1.9 volt. You got to make sure that everything that you have on there, your A to D, your microcontroller, all the peripherals, the flash memory, must still work. And that's an important point, because sometimes when you read a microcontroller datasheet, they say, this guy works down to, 1.5 volt. But then you go read the flash thing and it says the flash works down to, 2.3 volts. So the one is far above the end voltage of the lithium battery. If you find that out late in a project, you're going to go back to that $6 battery. And then last point there is, as soon as somebody tells you, well, that's easy, you just have to put in battery gauging so that you can monitor the state of the battery, your hair again should stand on end, because it's literally years of engineering work to do battery gauging well, especially when you do it over a wide temperature, because the battery performance is so highly nonlinear over temperature that almost any model that you use for battery gauging is not sophisticated enough if you want to implement it in a microcontroller. So be careful of that. The language side is fortunately very short. Here's the TIOBE C index. It's been leading for 12 years. Don't use anything but C or C++ to implement your language. Okay? If your programmer comes to you and says he wants to use Ruby or Java Beans or whatever, tell him, look, this is an embedded project. Go look at this page on TIOBE and sit down and implement C. That means your skill pool is large. You can get lots of people who do the work. You can find very good libraries, and you can find an excellent compiler if you use C. For all other languages, those are red flags. And I guess quickly, the developer. Your developer is more than 66% of your cost, right? The guys typically, one of the 70 million Generation Y guys that are walking around. Developer efficiency is extremely wide. If you get a good guy, he can literally be 5 to 30 times better than, a bad guy. So he's got to understand licensing. He's got to be aware of the fact that when you implement a library in your software, there's legal issues. Some of them will actually force you to publish your code if you use them in there. And several large companies have stepped into that trap. They develop something, they don't read the license agreements of the library, and then they're forced to publish their entire software piece. Make sure that you understand what your libraries, the conditions of any libraries that you use. Make sure that you have smart goals for your programmer, which means that they're specific, measurable, that they're realistic, that they're timely, and that they're achievable. And make sure that your programmer is reuse focused. In other words, don't let him recreate code that already exists. Force him to, as far as possible, to use the same code, or get a programmer that has already learned that, so that you don't have to manage him to do that. And then finally, if you have a team of software guys, you're going to run into the fact that one guy wants to, put the little curly brace there, and the other guy wants to put the curly brace there. And every time he gets software from the other guy, he changes all the curly braces. Then he goes back to the other guy, and he spends an hour, putting the curly braces back at the top, which is, terrible and extremely inefficient. So make sure, if you have more than one guy working on the code, that there's agreement between them to not do that type of thing and waste time and efficiency with that. And also, if you have more than one guy working on the software, make sure you have a submission process. So if somebody submits code, and there's lots of ways to do that, but that there's agreement on how do you revise code, how do you test the code, and how do you approve code. And then finally, just a few words on the tools. When you program for the ARM, Eclipse and the GNU-C compiler is typically what you get from a vendor to do that. You can literally get that from all the popular vendors. And it's a great compiler and integrated development environment. But actually, the most important thing when you get a set of tools is the libraries that go with it. And if you're developing a commercial product, the most important thing that you should ask and think about is the licensing. So there's a list of the ideal requirements for a license. It should be simple to read. It should permit you to modify the code without any fee. And you can read the rest of them there, but those are the ideal license requirements. There are very few license requirements that are that friendly. They go to the point where, up to the point where they force you to publish your code, etc. The point that I'm trying to make is you have to read the license requirements, and you have to select libraries that meet your needs and not get you into a point where you're legally forced to do things because you didn't read the agreement. Essentially, when you import that library into your software, you're signing up to, it's a legal agreement. You're essentially signing a contract with those guys to do whatever that license agreement wants you to do. The good news is that ARM has a library called CMSIS, Core Module Standard Interface Software. It's a great all-round library that ARM allows all their users to use. It's got an ARM-specific license, so there's still license requirements, but it's fairly permissive, and typically you can go implement commercial software with it. So it's a nice hardware abstraction for the CPU, the I/O, and all the debug tools there. That's the end of it. I quickly want to show, here's 4 typical evaluation boards from 4 popular vendors. The one in the top left is Energy Micro, which is now Silicon Labs, the Gecko. The top right-hand one, the small one, is NXP. That board is made by Embed, which I will show you a little bit later. Infineon is the red guy on the right at the bottom, and a Freescale board there on the left.